Hi everyone, hopefully you can hear me well. So I am Victor Pajuelo. I'm a lecturer at the Barcelona Technology School for the Master of Big Data. I teach a variety of subjects from data science to advanced analytics. And today we're presenting some of the research I did through the years before BTS, where I work a lot with satellite image processing for natural resource management. So hopefully you enjoy this webinar, and we are just maybe going to go through the whole presentation, and then we can have like a Q&A afterwards. All right, so today we will have like a small introduction to remote sensing and the concept of remote sensing, and as well their application to natural resource management, which it has been basically my task for the past 8 years from a research perspective, with three examples of seaweed monitoring, invasive species monitoring, and tree colonization. And also I will give like some ideas on how to get started with geospatial monitoring. All right, let's continue. So let's have a small introduction to the world of remote sensing and satellites. Basically, remote sensing, what we understand as remote sensing, is basically collecting information from an object without making any physical contact with that object, and that can be in the form of either radar technology, cameras, optical imaging, or microwave sensing, and so technically, if we take a picture or a selfie, that's in a way remote sensing. But in the context of geospatial analytics, the object that we are actually studying is usually the Earth, and as well for remote sensing, other type of planets like Mars, where the scientific community has done extensive work in the remote sensing field. And also that word or the word of remote sensing includes basically all the processing of the collected information from those devices. Remote sensing goes back towards to the first aerial images, and basically when we started realizing as humanity, or the scientific community started realizing the benefit actually of taking pictures from above, either through aerostatic globes or any other means. And the idea of mapping the space has been always there for research, whether we go not only for research, also for in terms of let's say artistic representation of space, dating back to even Stone Age, in the way which we communicated through cave paintings about our geospatial scenario. So basically, map making has always been with us, and remote sensing has been part of map making. But the field that we're going to discuss now, rather than map making, it's with the field of looking at and measuring directly from images that are taken afar. So one just a little introduction on what actually remote sensing is and where we started. As a small historic note, a few years ago, this type of satellites, we understand now remote sensing, right? We are understanding now remote sensing as sensing those images that come from satellites, but this can come in, as I said, in any type of form, whether that is drones or any other type of device that senses from afar. But the epitome, or let's say like the main sort of idea related with remote sensing, when we think about it as a scientific community, we think about satellites, right? So just for you to imagine from where we are coming from, we actually got some declassified satellite images from the 60s. And this was a type of satellite, the Corona satellite, which doesn't stand for coronavirus, but it's funny that the name goes in there. But this was a spy satellite from the US. That what they did, they carried on like cameras, like film cameras, to take images from different places in the Earth. And the very interesting thing with this is that right now we have satellites that actually transmit digital images through an antenna to our ground station. But before we didn't have that, so we actually, or they actually had to shoot the camera back down to the earth with a parachute when the film was ready, and then a plane will go and collect that camera. So the type of sensing that they were actually basically like performing was basically for spy scenarios, but they were also looking into basically mapping, charting, and geodesy. And there is now a growing trend on actually taking parts of these declassified satellite images that you can actually access if you just type or search for Corona Reconnaissance System, and recovering these images from back in the 60s to check the state of the world back then. Due to the analog nature of the images, the resolution is actually dependent on the type of scanner that you use to process those images. But typically the resolution is actually quite high. So you get very high resolution from a very old satellite in a very old time. So where you can actually basically look at how the world was back in the 60s. So you can use that for studying processes like environmental degradation and such. One of the interesting things is, of course, as a spy satellite, they were shooting back these cameras, and sometimes they landed in the wrong place. In this case, some Venezuelan farmers found a strange object thrown from the sky with consistent in a huge camera, which is part of the Corona Reconnaissance System. And it's just like an interesting historic note on how actually we were dealing with remote sensing back then. This is an example of the type of images that you could collect with that satellite. And this is the pyramids in Egypt. And due to the fact that many of these images actually were overlapping with each other, you could actually create 3D models. So researchers, what they are doing now is actually looking at how the biomass, or for instance, like glaciers are, what was the height of the glaciers back then, and how it has changed to nowadays. So we have an archive of information that we did not know existed until now, and now we can do some image archaeology in order to recover some of these images. By the way, I can put you in contact with some of the researchers that are actually basically working on that type of work for glacier basically estimation or volume estimation from the 60s up to today. But today, luckily, we are not shooting any more cameras back down to the Earth with a film camera. Basically, back in the 1972, NASA launched the famous Earth Resources Technology Satellite, which was renamed Landsat-1. This is like a mission system, a satellite system that actually stayed for a long time with the geospatial community. And most of the people that we started with this world maybe 10 years back then, we actually were using this satellite a lot in our assessments, as you will see today. And this sensor was basically a multispectral scanner, so it was not a film camera anymore. And basically that multispectral scanner consisted of 4 separate images, which scanned the Earth at 4 different wavelengths. And this is a very important concept in remote sensing, which is the concept of bands, right? So different channels that we have in order to actually study the Earth at different wavelengths, different parts of the electromagnetic spectrum. So one of the most revolutionary things from this type of sensor was not only the capabilities of sensing the Earth at different wavelengths, but also the capabilities of scanning every spot in the Earth every 16 days. Now we have massively improved that with other type of satellites, but back then it was like every 16 days. Now we can get almost daily imagery from the collection of constellations that we actually can access. So this basically the Landsat program was just like this, scanning the Earth like every 16 days. So you can imagine that we have data sets that go back to the 60s with the Corona Reconnaissance System, which are images scattered around the Earth. And then we have Landsat program, which goes back to 1972 at various degrees of resolution. Resolution means the minimum detectable object size that you can have detected at the ground range, and the various degrees of resolution that the Landsat has. The last ones had actually like 30 meters, which it was good enough back then, but now we have other type of satellites that go beyond that type of resolution. But you can imagine that, we are starting building like twin Earth with both with 3 axes, which is like, of course, like the spatial one, but also the time one, right? So we have a huge archive of information that we can access. As data scientists or researchers, we can use that to solve different problems and different questions. And here comes one of the most successful missions for the scientific community, which is the Copernicus program. The Copernicus program is sort of a reply to the Landsat program for part of the US, but the Copernicus is part of the European Union. And the beautiful thing of the Copernicus program is that it has basically opened for any researcher to actually mess up with the way we actually process this imagery. Back then, when we were working with Landsat images, we just had basically the image processed. As you can imagine, you have basically different stages in satellite imaging. The first thing that you do, let me share with this. If there is a satellite here, then you take an image of the Earth, and the first thing that you get is actually you get like the atmospheric noise here. So the image that you get, actually you are actually imaging the Earth, but with a lot of atmospheric noise. So you get different levels of products. One of the main levels is that when you capture a product, you can have usually it's called level 0, and this product is an unprocessed product, which actually it will not, if you actually watch it, it will make no sense for you to be working with from a data science perspective. But then you have the level 1, and this usually it relates to the top of atmosphere reflectance, which is like the values that you get here, being this the Earth. And then you have level 2, which is actually you do some atmospheric noise removal and other type of algorithms to actually get the reflectance at level 2. The problem with Landsat satellites, usually what they had, actually they had like a very close algorithm, let's say, as a pipeline. So you will not, usually the images that you will get will be images already processed. But with the Copernicus program, they actually released a lot of softwares out there for you to process any type of imagery at the level that you want. So there is softwares called like Snap, which is usually the one that we use. Sorry for that, it jumped to it, but that's usually used for basically pre-processing images with various degrees of let's say accuracy. But it's actually it opens the whole, let's say, like remote sensing for the whole community. So it's a very interesting approach to Earth observation. And we have different missions. We have a very interesting mission, which is Sentinel-1 and A and 1B, which is a radar mission. That's a synthetic aperture radar, which is a type of sensing system that what it does, basically, it shoots like basically electromagnetic on the microwave spectrum to basically like retrieve information from the Earth. So that actually bypasses clouds, but it has like a more complex, let's say, processing pipeline. But still, like it can be used a lot in conjunction with other optical systems. So optical systems, you can imagine that as a typical RGB camera that you have, all right, but beefed up with a lot of more sensors that it allows you to take images at different wavelengths, so seeing parts of the spectrum that we cannot see. And what Sentinel-1 is doing is actually adding another spectrum to that, but it's the one that actually can even, let's say, penetrate clouds up to a certain point. So you can see, like, let's say, even in a clouded environment. And then we have the most widely used, which is Sentinel-2, which is a high-resolution optical mission. High resolution, with the new constellations coming up today, like Satellogic and others, this maybe it's not anymore the way to go, but this is like 10-meter resolution, whether, Satellogic and other imaging systems, they have 1 meter or less. But this is basically like what the European Space Agency is offering for free. Then we have other types of missions, like the medium resolution imaging and altimetry mission, which is a coastal altimetry, more or less, mission. Then we have atmospheric chemistry missions that this is not yet launched. And then we have the Sentinel-5P, which is giving a lot of insights on pollution. And there's actually now some good studies on how the lockdown has actually affected contaminants suspended in atmosphere. So I urge you to actually look at some of those. And then we have different ones that are going to be launched soon, in, basically like low Earth orbit atmospheric chemistry mission and altimetry mission. But so far for data science, what is heavily used is Sentinel-1, Sentinel-2, and sometimes even more Sentinel-5P for the contamination or pollution, sorry. There are, however, other type of Copernicus contribution missions. ESA is a, let's say, like a weird conglomerate of different companies. So you can actually get access to different, at least like ESA is kind of contributing to this type of missions, which are atmospheric, optical, very high resolution, optical, medium and low resolution, SAR, synthetic aperture radar missions, and altimetry missions. And basically, this type of thing is that ESA is collaborating with, and some of them, I mean, you need to pay for it. Some of these images, but if you are a researcher in some university, maybe you can get actually access to some free data from some of these companies. All right. So regarding Sentinel-2, which is one of the things, or one of the actually the sensors that you can use the most for your benefit, due to the open access and because it's actually free if you're doing any type of research. You have three type of resolutions when the satellite has been processed. So you have 10-meter spatial resolution, and yeah, the 10-meter resolution, you have different bands, which bands, I mean, if you are in a remote sensing scenario, band, it's more or less like a channel, if you think about that, and it's also coined as well as dimension, if you think about NumPy arrays or Python or similar. So these bands basically image, this will be like, the typical, this will be like a camera, like an RGB, right? You have a red, green, blue, and then you have also like very near infrared at 10-meter resolution. And then we go with 20-meter spatial resolution, where you actually can image the shortwave infrared band 11 and 12, and also like the very near infrared. This is usually used for a lot of vegetation analysis and disease monitoring in plants and such. Then we have also the 60-meter spatial resolution, which is actually used for for coastal aerosols and different parts of this. And you need to imagine that then you have maybe like, if you want it this way, you have, let's say, like 4 resolutions if you want. So you have at least the X and Y. So I mean that's the spatial. So that would be one. Then you have the spatial as well, and then the spectral resolution, which gives you like the narrower your bands are, like the finer details you're going to have, and the more like wide, and the more you will be averaging across those nanometers. So then we have different sort of band, what is called like a band math combinations. So we can actually combine some of these bands of the channels that are coming from the satellite to actually create different maps that reveal, just by doing a band combination, they reveal different concepts. So we can have like a color infrared type of stack in which basically we can emphasize the healthy and unhealthy vegetation from it. And basically it is especially good to detect different types of chlorophyll status. And as well, we have shortwave infrared, which this can be basically the combination of this type of band maths. That when we speak about band math, is that you have, if you imagine the image as a layer, so you have one layer on top, which will be band 12, right? Then you will have another layer down, which will be band 8, and then you will have another, which will be band 4. And then you will put that into any sort of computer system, and band 12 will be read as red, band 8 as green, and band 4 as blue, right? And that's how actually we can depict type of images like this. So when you do that, then with the shortwave infrared, you actually can sense different darker shades, which will indicate different denser vegetation types. Then we have actually a type of band combinations that reflect agricultural activity, also geological types, using more or less like also the shortwave infrared, and bathymetric, which looks at the type of sediment suspended in water. That's very good, for instance, to study soil erosion processes. And then we have actually proper band math combinations in which we apply some algorithm just basically like indexes to our bands. One of the most widely used ones is NDVI, which if you are a bit curious about remote sensing, you might know that this has been there for quite a while, and basically what that is an index that relates band 8 and band 4, so near infrared and red. And what that does, it creates an index from, usually it's from -1 to 1. Being 1 like extremely healthy vegetation, 0, and from 0 to -1 being no vegetation. So then you can get like an assessment about the status of your vegetation. However, I must warn you that this index has been heavily used on the wrong way, because there are different reflectance properties of soils that affect this index. So it needs to be used with a lot of care when extrapolating, basically like assessments for your problem. And then we have also moisture indexes that goes along the same way. It's a quick band combination between shortwave infrared and infrared, and what it gives you is like a moisture content at the reflected level. But again, both of these NDVI and the moisture index, they are a good indicator, but I wouldn't take it just as a I wouldn't take this for the, let's say, like totally for real. When we need to actually do some heavy processing, then we actually we could potentially engage in other type of problems. So what I would do in this case, if I want to study vegetation, is go to more finer type of assessment through the biophysical parameter that ESA, actually the European Space Agency, recommends, which are leaf area index and other type of more complex indexes that you can find in the software from European Space Agency. And let's go now that we have a small picture of what remote sensing is, what type of satellites available are there that are kind of open for us to use as researchers. Let's look at the idea that actually I work with. People work with satellites in very different manners, for agriculture, for different types of services industry, for geology. I work mainly through my research period as looking at different natural resource management problems. So basically, thanks to this constant availability of satellite imagery, we can monitor these natural resources at a rate that we couldn't before. Basically, that means that certain parts of the world, you're getting an image every 3 days, maybe in other parts of the world, depending on the satellite, you're getting every 6 days or every 12 days. But it gives you a rate of imaging that you couldn't think about it before. So I will show you a list of different research projects that I have been involved with, in which we have used satellite datasets, amongst others, because we will see that it's not enough just with satellite imaging to actually perform accurate assessments on this type of natural resources, which are sustainable harvest rate estimation, invasive species monitoring, and ecosystem process prediction. So we will quickly see why I said that actually these satellite datasets are not enough to perform automated and reliable management of natural resources. So let's look at seaweed monitoring. So I did most of my, I'm originally from Barcelona, but I did most of my research career in Iceland. So there, basically, I stayed there for about 8 years, where I was conducting different research projects. And one of them was in this area in Breiðafjörður, in the Westfjords sides of Iceland. And there, what we get is some certain, mostly at the coastline, we get this type of environment. So this is algae, like seaweed. You can see already from this image that there are two different types of seaweed, which actually was a super headache for me. And the idea here is that the Natural Research Institute wanted to identify both the extent and the biomass of seaweed for sustainable harvest rate products. And we can see here, this is one of the flags we shall see like what we were doing there. And this is basically the type of things we wanted to look at and monitor. This one type of seaweed, and here we have another type of seaweed. It looks exactly the same, but it's different. So the idea of this is that this Ascophyllum nodosum, which is one of the types of seaweed, is very abundant on these Icelandic coasts, but is harvested for usually animal feed and also farmers and for other types of uses. And even if there is a lot of it, they need to know the sustainable harvest rate in order to maintain the balance of the ecosystem, because it takes a long time for this type of seaweed to grow. So it's very important to actually know what is the correct extent, both the extent and the biomass, which you can understand. You can think about the biomass as kilograms of seaweed per square meter, if you think about that. So in order to estimate those rates, the researchers need to know this biomass at the Icelandic shores and look at what are the sustainable rate for that problem. And usually, in a traditional manner, this accounting was done manually by actually what I mean manually is that someone will fly with a plane around here and look at all the type of seaweed that is there, and there will be someone in a computer doing exactly this. Okay, so this is one type of seaweed. This is another type of seaweed. I think it says here that my connection, internet connection is unstable. Hopefully you can hear me correctly. But anyway, so that means that you needed to have someone actually labeling manually these images in order to then account for the square kilometers that you have in seaweed. It will basically take about 6 months to adjust in this part of the Icelandic shores in the west. So this was an opportunity to use AI and a combination of remote sensing and AI to actually automate and ease the biomass estimation process. And as we will see, thanks to this collected information and the data sets generated, now it's possible to actually perform biomass estimates using the model I created there with other researchers under a time frame of just a couple of days. And some of the huge challenges we had in this project were like the short window of time for data collection that we had, because as you can see, this is low tide. So we only had few hours in which actually we needed to combine clear skies, so we could have a good image from the satellite, sorry. And really low tide. As you can imagine, in Iceland, having clear skies is not a given. So we have very few satellite images we could work with. And precisely because of this, we mentioned on low tide, and as well due to the limited optical capabilities due to the cloud cover. And also as well, you would say, hey, Victor, you have talked about SAR images that penetrates clouds, and that's right. But the problem with SAR images passing around that place in the Earth, at those latitudes, they pass at a moment where we could still use some of them to identify the seaweed at the higher part of the shores, but not the full extent. And also the existence of more than one species of seaweed, which actually complicated immensely the task. So and this is some of the locations that we actually did some sampling, and you can see here even more clearly, which is there is one type of seaweed and then you have another totally different type of seaweed there. We were interested about this one here. So and this is part of one campaign. So in order to actually get data, what we did, because there was no data present of this, I mean, we had some manual digitizing images, but they were dubious, and we talked a lot about them. So with a drone company called Swarmy, we basically we imaged certain areas of the whole coastline in order to get ground truth. And ground truth is this type of you can, if you think about that, those are the labels or basically that data set that you cling to in order to know exactly what is there and that your classification is being performed correctly. So we actually imaged we launched different missions with drone in order to look at the different scenarios. And for you to understand a bit the mindset of this project, if you look at this, you think of this conception of having the reality on one side and the low resolution satellites on the other side, we wanted to have like a link of the different spatial scales because we didn't have the data. So we needed to work with all of those and to estimate the biomass content and see which samples at certain locations and then hi, do you hear me? Or I don't know, like it looks like we went out. So this. Let me actually. We were. That I think you still like hear me. I'm not sure if you. So basically what we had here, it was that we could, in this case, let me see. Okay, you can see the presentation now, or not? Let me see. Okay, all right, I have control of this back. So this is the point here, and you can see here that is actually around this area here. So you can see that this image that was taken from the ground was around this area here. So basically we wanted to link ground truth from points, samplings that we will take, that the research team will take around, looking at the biomass of different parts of the image, and then upscaling this to basically sentinel. This is a sentinel image, so you can imagine the downgrade in resolution. So you go from seeing very fine the two different types of seaweed here in the drone image to this. So this is actually a very challenging problem to identify the total extent of one species in respect to the other. And then we had the low resolution satellite of Landsat. So this is Landsat, sorry, and this is Sentinel. So the idea was to actually link all together through ground truth, so we'll know precisely in this point what type of seaweed there is, the amount of biomass, and that will be the same here, and that this will be the same here. So we could actually create a model to do upscaling techniques and subpixel classification. This was a very challenging task due to the type of dataset that we have. These were actually the sampling points that we had. So we had different total of no more than 6. Even there was another drone flight that didn't go very well. So no more than 6 actually data sets from the ground. We had a lot of more like point samplings scattered around from the Marine Research Institute, where they were actually telling us the biomass content at different points of the shore. But the problem of this was basically that we actually work with the Marine Research Institute in order to get a good, let's say, like variability on the types of distribution of both species in all the sampling points. And as well as like we had a lot of biomass measures collected at each site and GPS locations of different types of seaweed. And also we made sure that when we were flying drones, at the same time, we were flying them at the same time that the satellites were passing by. So we actually had a good idea in terms of, like what was the status at that day for that type of seaweed. And the challenge was huge in terms of, the tide. This is one of my colleagues back then that we were actually setting like permanent plots, because of course you can see we will go there, you find this perfectly clouded, and then your day is ruined. And then the only thing we could do is fly drones in order to actually get some data and maybe perform some early classification. And what we were doing here basically is actually setting point measurements so that we could go back and do another imaging with a drone exactly at the same point when there will be no clouds in sky. And this is actually the way we actually measure correctly, like the location. We will use this flag, which is a ground control point, and then in the images that we will take from the drones, we will actually locate this point to the image in corresponding image. So we will actually geo-reference and will be correctly placed in the map, the image from the drone and aligned with the satellite images. And we were using a GPS rover and a base station that we will put some here. And as you can see, we had a lot of fun because we had to actually traverse down to places actually the Marine Research Institute told us that we should go there. So sometimes those places will be really far out, as this one. And it was a bit difficult. I mean, so usually, I guess, as data scientists, we don't know how hard it is to collect ground truth, and we don't value that amount of ground truth. Believe me, after the project, I really valued the work that people in the field are doing. So I value every bit of information that I get, and I try to make the most out of it because it's hard. So we actually were traveling around all these areas here just by foot, and there were quicksands, mushy ground. Also the tide hours, we need to look at that. Yeah, a lot of flies actually. So this is again some more of these images. So this is like what you could see from the ground, and this sort of reality, this part of reality, and this idea of the ground truthing turned into this, an RGB image where we could actually pinpoint and look at exactly what was going on there. And after that, we will classify those images using basically like a semantic segmentation network like UNet or similar. And we will have that classified image that we will use as a reference. So I know that this will introduce error in the system, but we have no other way to do that. So basically, we will know the distribution of species thanks to the UF image. So we will know for this pixel what was the for this pixel what was the distribution there in Ascophyllum. Maybe it was here 90% and 10% of the other type of algae, and we will record this this data. So we could do like a statistical distribution modeling later on. So those UAV images taking as the ground truth, as I said, were passed to a UNet network, and then the semantic segmentation then was also applied to Landsat and Copernicus mission systems. So basically, we will use those data sets as labels in the ground, and we will make sure that actually they were clean enough so we could actually pass them to Sentinel. And then the test results were compared over manually digitized image, which were downscaled to Sentinel in order to be compared. This was the distribution calculated for Landsat, and then the mission for Copernicus. So the final extension calculated was about 130 square kilometers of seaweed. That's a lot of seaweed. But basically that was not enough. By knowing the extension, we actually needed to do a further step, which was a regression in order to predict the distribution and the biomass of both species, because actually this segmentation was many times actually just classifying seaweed as such. So then also we needed another network in order to actually know what was the potential percentage per pixel of one seaweed or another. After correcting by that value, we will get a value that was an accuracy that was close to 89% compared to manual digitized images from the Marine Research Institute. And just for you to give you an idea, the total inference time, that means the time that takes once you have the model then you can actually do some predictions over some new images. So basically, counting also the conversion of all this to a polygon, which was the type of data set that they want to actually have in the Marine Research Institute, was basically 2 days of maximum processing. So we have 6 months to 1 year for 2 persons versus a weekend of processing. So that was like huge and started opening the eyes of the Marine Research Institute towards artificial intelligence. So basically, they right now have a tool where they can predict and assess the biomass estimates over the whole country under basically a couple of days. And we were also very careful in order not to kick anyone out from their job. But basically, the people that were previously doing that stuff, then what they end up doing was testing and checking that everything was actually according to spec, and keep on sending ground truthing in order to improve the model when necessary. All right. So this is an example of how to use very scarce data and let's say build up a system that it works and that gives some insights. And basically, it's maybe at an accuracy level that is below what human could do, but the automation is insane, right? You don't spend half a year just digitizing in front of the screen. You just run it for a weekend, and then if you want, you actually can improve it manually after that. Let's look at another type of research project that I work with, which was invasive species monitoring. Again, this type of monitoring was set for the whole country, not just a part of the country. We were looking at this beautiful plant. So this beautiful plant is called Alaskan lupine or Nootka lupine, and is a type of plant that was introduced in Iceland in order to avoid this. Iceland has a huge problem with the certification an island in the middle of the Atlantic for infrastructure, but also in terms of health, right? Because you have microparticles flying around. And as well, basically, you're losing soil. So you wouldn't like to lose a lot of soil if you're on an island, because you basically will get out of any type of resource at the end. And the way it works is that you have this beautiful looking plant. This is a good idea because it was a plant that was thought as a pioneer species. A pioneer species is a type of plant that basically prepares the grounds, right? Basically, this is a rocky area from a glacier. Okay, do you hear me? Hopefully you will hear me now. I can trace back to here. Basically, I was just pointing because they're telling me that my audio is getting lost somewhere. All right, so I will start from here. So basically, we were looking at this studying this type of plant, which was introduced in Iceland in order to avoid these dust bowls, because Iceland is a country where there is a lot of desertification and soil erosion processes. So this species was thought about like pioneer species. Basically, they prepare the ground for other species to come. So this is a gravelly glacial swamp area, provide the necessary nutrients for other species to colonize this. Okay, this actually was a complete mess up because this plant basically turned into this. The plant took over the whole country. It's taking over the whole country and is now considered all right. Let's share screen again. Do you see my screen now? Sorry for that. If I checked that was not also loading a satellite image. Hopefully that is correct now. Okay. I'm sorry, I have unstable connection today, and it happens. So basically, what I was talking about it before we got lost into this is that this type of species introduced to bind the soil to avoid that the soil will fly around. All right, I'm very sorry about this. Hopefully now this works. I think, I mean, I should be the only one connected to my Wi-Fi, unless my neighbor is stealing my internet. Could be. All right, hopefully, yeah. Okay. So basically, what we have is that this type of plant was introduced in Iceland in order to introducing the species in order to actually basically bind the soil. Basically, what happened is that this species was fixing nitrogen in the root plants, and it was outperforming native vegetation. So what happened is that it took over many already healthy vegetated areas, not only barren lands, but also healthy vegetated areas. So it was destroying species that were Icelandic species and Icelandic ecosystems. So the eradication of this plant is extremely costly because the seedlings are easily spread, and when they actually when they grow up to this point, they basically they're almost impossible. It's very expensive to eradicate all this. Also, because if you cut the plant, then it will regrow to next year. So you need to take the roots out. So the idea is to actually eradicate it early. So then the Soil Conservation Service started this in a similar manner to seaweed. Look at what is the current extent of looping. Let's study what is the current extent, and let's create a model that can be used both to assess the current extent and detect new spreading locations as they come. But of course, they were doing this in a manual way. They were digitizing manually. So we came in with help of AI and satellite imagery in order to help with this endeavor. But one of the main challenges here, is one of the main challenges that you will face if you go into this geospatial market, was the lack of labeled data sets, so the lack of data. So you can have a lot of data, but not a lot of labeled data sets of the data set that you actually want to work with. And as well, the cloud coverage that is coming with new imagery, and the fusion of optical and SAR imagery, for that. So the generative data set, what we work with was basically we have point locations similar to what we'll have with the biomass in the seaweed. We'll have point locations everywhere. And then from these point locations, we will know that there was looping. So then we draw like a 500 by 500 meter square box around every point. And then manually, and this was manually, I mean, me, the one who is speaking, was actually digitizing this manually and using also like region growing algorithms in order to extract the information and get at the end with something like this, which is a shape of the looping. So then when we had something like this, we had our data set finalized. So we had a data set of a pair of data sets with this 500 by 500 meter tiles paired with looping content in those images here and here, here and here, and then scattered around whatever we actually had Do you hear me now? I guess. I think I have a problem now sharing my screen because I got kicked out of the meeting, I guess. Let me see if I can fix this. I will actually. All right. Christina, could you kick because I joined 2 times and I cannot present now. So if you could kick the other one. Okay. All right. Thanks. Okay. Sorry about that. I guess we're hearing so is maximization based on this rapid all right, audio is missing. Do you hear me now or not? You hear me? All right, hopefully you hear me now. All right. Okay, let me try with PDF. Maybe it works better. I think might be also PowerPoint. Who knows? Okay. All right. So we were here using UNet, like in other cases, and we were using rapid tiles for basically looking at this type of satellite back then that was 5 meters, and we had like our prediction and then our ground truth. And from there, basically, it took us for a GPU like an NVIDIA Tesla B100. It was a total training time for the whole country of 12 hours. And the total inference time for the 125 rapid images was 18 hours. And at the end, we had a total detected, similarly, actually quite funny, of 130 square kilometers of looping detected over those images, at least over those images that which were not covering the whole country. We only had 125. And then the model output was saved and used as training labels for Sentinel-1 and Sentinel-2 imagery in order to actually retrieve the capabilities of creating an automated system. And then this was some of the results that we got. And you can see that these images from RapidEye that we trained on was 2012 and 2011, and the image in the background is 2018. And basically, some of them you can already see that the looping, this is looping that was outgrowing the previous stages. And in this case, this is the middle of the country, and it was kind of okay. But here this was one of the worst cases where they actually planted looping back in 2011, and it was just spreading through here. And this was what was planted in 2011, these small stripes. So with this, we could actually image the whole country and look at what was going on. And you could see already here this image from this classification of 2011 and the expansion of the Seaweed on 2018. The idea of the research project as well, it was to actually then as well classify 2018 and look at the percentage of spread and potentially look at the rate, both the rate at what is spreading and where it is spreading. And you can see this image, you can see in this image like a very interesting fact. This was one of the typical sun plains where the dust balls were created. And you can see this looping lines actually planted back then, right? So again, I repeat, the background image is 2018 and the data we work with was 2011, right? So the data represented here in purple is from an image taken in 2011, and this is the 2018. And in 2018, you could see that what was planted before was already spreading everywhere here. And here, this line that was planted in 2011 was already spreading. And you can see like the method of spreading. So you could see here that the looping also was carried through the rivers down the stream. So even if you had looping here, was not only carried by wind, but also through the river, to the riverbed. So the second part of this research project was actually to detect the potential spread of all this to other areas. And let's go to another example of tree colonization. I know I'm almost on the hour, but I would like to finalize it, and hopefully I don't have any more internet problems. So this was a type of another type of let's say like monitoring system, which was developed in order to track Arctic greening. So usually what you will have in these glacial samplings, that is one of the biggest glacial samplings in Europe, is that it will be everything completely barren, right? So everything will be kind of like this, like completely black, and almost no vegetation will be growing there, not unless the vegetation that you plant, right? So what you will be getting there is that you have like a huge sampling where basically people thought that nothing was growing until we had this system, or this occurrence. So this was the glacial sampling seen from a mountain nearby, and this was what you could see. So you could see a lot of moss and a lot of small shrubs and birches growing. So then people started actually looking at the ecological succession of the glacier retreat, right? So how the glaciers actually are retreating, and actually how the vegetation is taking over, and how the Arctic is getting greener, which is a way to understand as well, like the Arctic actually is getting as well warmer. In this case, it's a type of glacial samplings are a perfect place to study all the species colonization and settlement. And there was this growing trend of birch trees that actually were growing there in a very strange patterns, following following ravines and old moraines. A moraine is what the glacier ends up having living as a little mountain after receding. So it was a perfect moment to study what happens when glaciers actually retreat, right? So what happens to the ecosystem when glaciers retreat? So a lot of things happen, right? There's a lot of landslides, there's different type of things happening, a lot of kettle holes happening that we will see, but as well, what is happening with the vegetation? So the idea was then to use a combination of UAVs and artificial intelligence processes to uncover the density distribution, as well the spatially related variables that makes the birch actually, and this type of trees to go there. And the generation of this dataset was extremely complex because of the area is very, very, very difficult to access, and it's prone to constant changing weather. So sampling is very difficult. So basically you get like a 360 degrees wind. So you start in the morning, the wind comes from the glacier, rotates to the sea, and then goes back to the glacier. So it's kind of insane, a lot of high winds. We had also limited UAV coverage, and then we also had like a non-coherent data set from a reflectance point of view. We didn't collect multispectral images. We didn't have enough satellite data, and we had a total lack of label data. We didn't know what type of data sets we had there. So this was me back then with Swarmy, or the company that actually managed the flights to go there. So we were imaging with this type of planes all over the glacial sampling in order to get a very accurate image, cloudless, at a high resolution, to look at how trees were spreading across the sampling. This is me in field research. So you rarely see, well, I wouldn't call myself a data scientist, but you rarely see a researcher dealing with computer programs drinking coffee out from a tent. So there I was with my colleagues. And this is the type of images that we took. So these are beautiful images of the sampling, and you can see the structure of the bedrock there, which is basically a huge sampling. And scattered with mossy vegetation and the very different types of vascular data. And what you can see here, these craters that look like a crater from a bomb, that's basically when the glacier recedes, an ice block gets trapped into the sand, and when the ice block melts, it creates this hole. So actually, we also study the different spread of seedlings through the wind, and you can see that there is some spatial relation on where the sun is hitting, where actually the moss is growing, and what type of spatial and vegetation distribution is there within the kettle holes. So you see this oblique image, a perfect example of that, of actually how moss travel through all riverbeds in the area, and how kettle holes provide like some shelter for some type of moss. And we have this very, this very unique pattern distribution in which you can have like trees growing in all riverbeds. We wanted to study whether actually that's because of moisture, because of the wind travels faster there, because the seedlings actually have easier time traveling through there. Also, one of the hypotheses was might be because of the ice, because if this is moist there, then it actually gets frost during the winter, and the seeds can spread further through there. There were many hypotheses, and we used partially AI and remote sensing to solve some of them. This is, the type of also image, a little bit like RGB images that we collected there. So this was the data set that we collected. This is the glacier will be here in this area on the top of the image. And this was like a 5 centimeter per pixel image of more than 130 gigabyte data set collected. And this was collected, it was a different drone flights collected through a whole summer. And with varying light conditions, and we only had RGB imagery, because if you can imagine, we could have the most beautiful data set corrected for reflectance, that means corrected for incoming sunlight, which will make easier for us to classify vegetation there and using multispectral. But it was so hard to actually get images there, because you will be launching the drone will be flying for 30 minutes in the sky, then you will land it in the middle of a barren area, and then you will 5 minutes after pouring rain, snow even, and then you will need to pack everything, wait for the rain to go, the rain goes out, then you launch again, and like this. So it was extremely hard. And then we had the students from the University of Iceland helping us with tracking and tracing where the trees are located. So they had like a GPS system with a rover where they could actually pinpoint the GPS location and the different actually type of vegetations there. Then, of course, we had our georeference units for geolocating the image. This was me and a colleague actually setting up control stations so we could actually go back there and assess the changes through small areas for drone image collection. And this was our system for GPS as well, like locating the different pinpointing the different type of trees. And you can see this is a vascular tree, and this is the type of trees that are growing there. So at the end, what we did, this was like an extremely tedious digitization. Like we got back our data set from the students, and after hours and hours of podcasts from my side and tons of coffee, or a lot of liters of coffee drunk, we had a somewhat okay data set where actually we took tile by tile, and we were actually using region growing algorithms and basically like digitizing manually every little subsample, every little tile. So we will have our data and our label images. And this was hard. As you can see, the label images were not perfect. So we actually had to set specific loss functions to account for missing data within the image, and so that this will not affect the CNN. So the CNN that we developed was quite okay, quite fine, and especially looking at the different classes, which we did classification of sand, moss, vascular species, that means different type of trees, and birch, which was what we were interested in. And of course, not perfect, but it was good enough for actually getting getting an idea of where the sampling is going. And after that, we could actually derive in the area, of course, by looking at the center of the polygons and doing some heuristics. And once we had the density calculated of the trees pinpointed in the area, we could then go and take other drone flights which are actually closer and get up to 1 centimeter pixels to look at the spatial distributions of the other species involved. So the other part of the research was to actually, once we know, and you can see here that there is a gradation of the sampling plots, we created 5 more sampling plots, which we imaged during 3 summers with RGB, thermal, and multispectral cameras. And that was done so that we could actually calculate soil moisture indexes, thermal capabilities of the soil, and actually classify at the minor scale what other species are involved, and do a similar sort of modeling that we did with the seaweed. And you can see this is what I was talking. You can see the lines of vegetation here. This is line because they are through that area. So we also modeled that out. And basically, the status of that research project is that the spatial distribution model was corrected by the local variable. The sampling. What is going to look like in the VMs and other type of hopefully you hear me now again. I'm just finishing up, so I mean, this is basically the part involved in this research. I mean, it was not me alone. We had collaboration from the company Sparmy and the Marine Research Institute, the Seaweed project. For the lupine was Sparmy and the Landgrasland, which is the Sea Conservation Institute from Iceland. And the algorithm development was entirely led by me, and the project was funded by the Icelandic Marine Research Institute, Landgrasland, and the Icelandic Innovation Grant. So yeah, if you want to know more about these parties involved, you can look at them. Sparmy, Landgrasland, the Marine Research Institute of Iceland. Some of them other projects, but yeah, they will come up soon as I have the time to write them, because I got a baby recently and it's hard to actually do that. And if you want to actually go to know how to get started with your geospatial monitoring, you can go at the Copernicus data website, the sci-hub-copernicus.eu, and you can download any type of the Copernicus mission data there. Also, you have a lot of data from Catalonia in the ICGC website, and the essential Python libraries that I would recommend to actually learn by heart are Fiona, Shapley, Raster, and GeoPandas, basically because most of the work that you will do will not be with TensorFlow or PyTorch, will actually be with the ETL process. And everyone that has been working with geospatial data knows that the painful part of the process is actually getting all the data ready for being analyzed. So up to here, this was the presentation. And if you want to contact me, you can use this couple of emails, the personal one and the one from the university. And I can put you in contact with any people involved in the research if you were interested about the data sets or the applications. Yeah, so just send me an email if you need to. And I'm sorry for my internet connection. I will stop sharing. So basically, I stop using bandwidth, and let's go for the Q&A if you still have time. Do you have any questions? You can just mail to me if you have any questions for that. Well, I guess there are no questions. So yeah, just I guess I'm not sure if you, Christina, can see. I cannot see any of the. Let me see the chat, perhaps. Let me see where I. I actually cannot see the question. So if you can just send it to me, Christina, because I cannot. All right, thanks. Yeah. So to reply to Lenin, so yeah, this was incredibly. It's a very good question. He is asking, as in most models, the context knowledge of the terrain in the case of related dynamics involves a great effort. Can you tell us about how the effort of a project like this is divided in percentage in the phases of data acquisition, data preparation, exploration, and data analysis? I can say that data acquisition and data preparation is pretty much 70% of the time. And then what is data exploration is very minimal. I mean, I would say maybe, yeah, 10% of the time, and then data analysis is the rest. But the most goes to actually prepare everything, do actually the not the analysis on the data, but actually preparing, doing the design on the data set, on the problem, basically. Is you need to take it like a business problem. You need to do the design for that in order to actually reach your goal. And that definition of the design and preparing all the data preparation, that's about 70% of the time. So when we speak about data science and AI, in these cases, is pretty much the lesser part of the project. What algorithms for precise classification have we used most frequently in the projects? The most frequently used by this is usually random forest, is what I've been working a lot with, and SVMs. But then there's a whole range of neural networks that I have been applying from UNets, semantic segmentation like segnets, and also ResNets for different type of problems. And usually those are the most widely used. Yeah, so these are kind of the things that I used most often. As well, like, before that, there is a lot of other things involved, like principal component analysis and other type of stuff to look at the data set distribution and also look at how perhaps you can take out some of the channels, right? So like, how can you maybe take some data out that actually is only bringing noise to your problem, to your algorithm? But yeah, but this is like, so far I am not, let's say, I am just on the process of writing these papers. I'm not doing the research part anymore. So let's say back then for 2019, I was using state-of-the-art neural networks. Right now, I guess they are not state-of-the-art anymore because the field is advancing so much. But yeah. Do you have any other question, or? I could see now the question and answer, sorry. Yeah. All right, so I guess we just close this. Thank you for attending, and hopefully this was interesting, even if we had a lot of problems. I apologize for that. I thought my internet was stable, but I guess I need to apply some artificial intelligence to know who is spoofing my internet, if some neighbors are actually behind that. And yeah, just thanks for everyone, and just send me an email if you're more interested about this, and if you want to be updated for the papers when they come up. All right, so thanks, and see you next time.